So today, or in this segment, let's take a look at chapter 43. Let's get a start on chapter 43 for the day. This is elementary particle physics. The picture that we've got here to start the whole chapter out, that's a particle detector. So when we ask the question of what kind of particles are things made out of, for the past 100 years or so, it's been pretty good to say electrons, protons, and neutrons. But it turns out that there's more complexity than just those particles. So we want to see how electrons, protons, and neutrons fit in. Along the way, in our topics that we've looked at, in addition to the electron, protons, and neutrons, we've talked a lot about photons. You could almost call this course a whole course on photons and how photons interact with different materials, and neutrinos. So now what we want to do is look at kind of the comprehensive picture, what we call the standard model for particles and particle interactions. So this is reality. And along the way, we'll talk about some of the evidence that we have. So first of all, some of the machines that we've used in making these observations are particle accelerators. And what this slide is telling us is that early on, researchers could actually do measurements of high-energy particles coming in from outer space. We didn't know how to generate our own high-energy electrons or high-energy protons. But the sun produces a number of high-energy particles and other things going on, other stars and different processes going on in the galaxy. And so some of these high-energy particles, they're called cosmic rays. They're really electrons and protons and such coming through Earth's atmosphere. It was observed, you could actually see some of the reactions with these particles taking place in our atmosphere. So eventually we learned how to use high voltage devices, bring particles up to really high energies, and run our own experiments in high energy particle physics. Now what they're pointing out here is quantum mechanically the wavelength of particles depends on how much momentum they have. And if you remember back to the chapters 34, 35, when we were looking at light, we said that the shorter the wavelength of a particle becomes, the better that particle is able to resolve detailed information about whatever it's running into, whatever it's interacting with. So in some sense, as we go to higher and higher particle energy, we can actually map out more detail about particles' properties. So for example, by the 1960s it was very obvious that the protons and neutrons were not truly fundamental particles. Proton and neutrons began to show indications that they were composite particles. They must be made out of something else. And by going up to very high energies with electron beams and firing electron beams at extraordinarily high energies at protons and neutrons, the way that the electrons scattered at those higher energies enabled us to figure out how many particles were present inside the protons and neutrons and what the properties were of those particles, and that helped to develop the quark model that is now part of the standard model. So our current understanding is there are quarks, particles more fundamental than the proton and neutron, and 3 quarks of different flavor and color, we'll talk about that, make up the proton. 3 quarks of different color and flavor make up the neutron. So what we're going to do here is, I guess, a couple of quick calculations. Here it says that we're going to take electrons, we're going to bring them up to higher and higher energy. So we're going to bring them all the way up to a kinetic energy of 1.3 GeV. So the G here that's 1,000 MeV. That's 10 to the 9th EV. So we're going up to even higher energies here. And it's asking, what are the wavelengths of the electrons going to be like? Would these electrons be able to map out the inner workings of a proton or a neutron? Now, these experiments based on this were actually run at the Stanford Linear Accelerator Center down the peninsula in Palo Alto. It's a U.S. national lab, the same as Lawrence Berkeley National Lab. They have a 3-kilometer long linear accelerator that brings electrons up to high speed. And the first experiments that were done there were taking these electrons and running them into basically hydrogen targets, liquid hydrogen or something, running electrons in and seeing how the electrons scattered off those protons. And from those experiments and from the scattering patterns, they collected evidence showing that the protons and neutrons were composite. All right, so in terms of resolution, let's get that answered here, or set up, I guess. So the wavelength is going to be Planck's constant over the momentum. And we said that we can do that in shorthand using hc over pc. So let's step over to the right side here. So I did kind of the resolution stuff on that side. And on this side, I'm pulling out all of our relativity formulas because these electrons are going really fast. The kinetic energy, it says that we're going to give these electrons 1.3 GeV. Now, just to let you guys know, we now run accelerators at 100 times or 200 times this much energy. So the highest energy electron accelerators now are much higher than this. This would have been comparable to some of the early experiments that were done with electrons fired towards proton and neutron targets. So here's the kinetic energy. Now the mass energy of the electron is in GeV. It's like 0.000511. So that's really small. And so the kinetic energy is now so large that the mass contribution is basically negligible. So if we were to calculate the total energy of those electrons, that would be kinetic energy plus mc squared, and it still rounds off to 1.30 GeV. And if we were to calculate the momentum, which we're going to need to determine resolution, well, momentum is e squared minus mc squared squared. But again, the mc squared squared part just drops out. It's negligible. So for a really fast-moving particle, something where the kinetic energy is much, much larger than the mass, for those particles, the kinetic energy, total energy, and momentum times c are basically the same. We saw this with photons. In the case of photons, where the mass is equal to 0, kinetic energy, energy, momentum, they're all the same value. So these high-energy electrons are becoming like that. In fact, from the values that we have here, we're able to go in and determine a value for gamma, and the gamma here works out to be 2,545. And if we solve for our velocity formula from relativity, these electrons are traveling 0.999999923 times the speed of light. And that's something we saw in relativity. As you get closer and closer to the speed of light, you're still picking up more and more energy, but you're asymptotically approaching the speed of light. The velocity is not necessarily changing by much, even when the energy is changing by a lot. So we can pick up this PC number that we calculated. We can plug that into our formula here, and we can take our 1240, MeV seems appropriate, so we'll say 1240 MeV femtometers divided by, so 1.3 GeV would be 1,300, that's a 1, 1,300 MeV, and so that's giving us a wavelength of a little less than a femtometer, 0.954 femtometers. Well, that's going to give us a resolution that can look, basically it can look inside a proton or a neutron. Remember, protons or neutrons have wave functions that spread out maybe a couple of femtometers, and so this is getting down to the scale where you can begin to see effects of the composite nature of a proton or a neutron. So that's the idea with the accelerator experiments that we do. Now, some of the very earliest accelerators were actually kind of handheld devices. They weren't very big, and they were developed by Ernest Lawrence here at UC Berkeley. So if you visited Lawrence, the Lawrence Berkeley, the science building up on the hill, the Hall of Science, the Lawrence Hall of Science, they've got this there in one of the cases. You can actually see some of these early accelerator, kind of handheld accelerators that Ernest Lawrence developed. So what Lawrence did was use magnetic fields to have electrons or other particles, protons I guess were more common actually, they would travel in a circular fashion in the magnetic field. And then what Lawrence was able to do was alternate the voltages, so every time the protons crossed from one side to the other, they got a little bit of a boost. And as long as the magnetic field's holding them in place, and they get a little push every time they cross between the two sections, they just keep going faster and faster. And so Lawrence was able to bring these protons up to higher and higher speeds, and then as they came up to higher speeds, move to larger and larger radius trajectories, and at some point they could exit and be pointed towards some kind of a target. And running things into emulsifiers, basically photographic plates, for example, and seeing what kind of reactions were generated inside those gels. So there's the external beam leaving. So that's kind of a history. This is something, I guess, this goes back to physics 4B, looking in magnetic fields. So for a charged particle in a magnetic field, this tells us the frequency at which the particle would be circulating. Now, as we built larger and larger accelerators, here's one outside of Chicago at Fermilab. You can see now that the modern day accelerators are miles in length. So these are really, really extended. And instead of just having one local magnetic field the particles are moving around in, what we do is we build magnets through all of the tunnel. So there's a tunnel here with a beam pipe inside. Protons are being accelerated and then circulated in one direction. Antiprotons are being circulated in the other direction. And the magnets are used to steer the protons and antiprotons. So at designated locations, they cross. And where they cross, there's the possibility of setting off some kind of a reaction. Because of the high kinetic energies of the protons and antiprotons, this enables those reactions to generate particles of much higher mass. So using protons and antiprotons, you know, we could generate particles with 100 or 1,000 times the mass of an individual proton. This is just showing how some of the acceleration can take place, at least the initial accelerations. What we can do is alternate positive and negative regions, create bunches of protons, and then as the protons go through, they get pushed, and then as they come to the next section, we switch polarities, and then they receive another push from the next segment. Here is the Large Hadron Collider, which maybe you guys have heard of, maybe not, that straddles the border. Part of it's in France, part of it's in Switzerland. It's near Geneva, Switzerland. And I guess this is the world's largest accelerator right now. You know, there was this superconducting super collider that the United States was planning on building back in the 1990s. And it struggled for years trying to get funding. It got the go-ahead, and so part of the tunnels were built. and then funding was taken away. It was determined that, at least by Congress determined the funding was just going to be too expensive. And that would have been, I think, more than twice the diameter of this, and would have gone up to much higher energies. So this accelerator goes up to 14 TeV. T is tera, so that's is trillions. It's 1,000 beyond the gig. So we went from MeV to GeV, and now to TeV, which is thousands of GeV in terms of energy. So the possibility of generating particles 1,000 times the mass of protons. 14 TeV, so a little bit beyond that. Here's another example that we can run some numbers on. So the question becomes, well, if I build an accelerator, how much energy am I going to have to use to bring these particles up to these really large speeds? So for example, if I bring a particle from rest up to 90% of the speed of light, how much energy would that take? Now that sounds like a special relativity problem. And then if I get all the way to 90% of the speed of light, and then I want to bring it up to 0.999 the speed of light, how much energy is that going to take? So let's take a look. I think we can go back to our formulas from special relativity and set this up in a way that is pretty systematic. So here are the speeds they're talking about. They're talking about 3 different speeds. The first speed is at rest. That was easy enough. So 0.0 times c. And then the next speed they're talking about is 90% of c. And then this is like 99.9% of c. So those are the 3 speeds they want us to consider. Now, in order to calculate energies are not going to be so much directly related to speed. In fact, they're not. What energies depend on is gamma. So what we want to do for each of these speeds is determine what's the gamma factor, because the gamma factor is going to tell us how much kinetic energy those particles have. And the kinetic energy that they acquire is going to tell us how much energy we're going to have to put into those particles to bring them up to those energies, to those speeds. So the gamma factors for a proton at rest, any particle at rest, the gamma factor is 1. And to bring a particle up to a speed of 0.90 c, well, the gamma factor is going to go to 2.29. Now, if we use our kinetic energy formula, where the kinetic energy is gamma minus 1 times mc squared, well, that tells us for a proton, now this would apply to any kind of particle, but for the proton we're going to put in the mass specifically of the proton. And what we find is a proton at rest has no kinetic energy. To bring it up to a speed of 90% the speed of light means bringing it to a gamma factor of 2.29. That means an increase in the gamma factor of 1.19, and that corresponds to 1.12 GeV. So a little over 1 GeV of kinetic energy in order to bring a proton up to 90% the speed of light. Now, in order to continue to accelerate that up to 99.9%, and you're thinking, well, that's not that much faster, the gamma factor actually climbs to 22.37. So that says, if I look at the difference in the gamma factor, and the difference in the gamma factor is going to tell us the difference in energy that I need. From going from rest to here was a difference of 1.19. Going from 90% to 99.9% brings us to or increases the gamma factor by 20. So that's almost 20 times as much energy. And we can see down here, putting the numbers in, that worked out to be, I'm going to have to check, I don't think that calculation's done quite right. I got to come down and check that number. That shouldn't be exactly 20.1. It should be a little bit lower. But in any case, this is going to become, so double check all of these, but this is the number that looks most suspect. So take a look at that. But yeah, what it's saying is to go from here to here, 90 to 99.9%, is going to take, roughly 20 times as much energy as it took going from rest up to 90%. That's how relativity works. As you get to higher and higher energies, the energies just keep going up. But the speed asymptotically approaches c. So in some sense, it's not hidden energy, but the velocity doesn't become a very good indicator of how much energy you've really got. The gamma factor becomes much more reliable. All right, well, let's get into the Standard Model. Let's talk about these fundamental particles and what kind of properties they have. And what this picture is showing is that along with the fundamental particles, what has to become part of our Standard Model are forces. So there are forces in nature. Now, if we list the fundamental forces in nature, it's like gravity was the first one we started off with. And it turns out we still don't have a quantum version of gravity that makes sense. So we don't have an accepted quantum description of gravity. So gravity we're going to set to the side. The Standard Model doesn't include gravity. What the Standard Model includes are electromagnetic forces. We do have a quantum version of electromagnetics. It also includes what's called the weak force and the strong force. Those are forces that we've talked about in the nuclear physics chapters. We've looked at the strong force and the weak force. And then there's an additional, I'm going to call it a force. It typically does not get presented that way, but if you guys have heard of, maybe not, the Higgs boson. It was a big deal when it was discovered probably 8-10 years ago, I'm guessing. And we'll talk more about what the Higgs boson represents, but we could talk about the Higgs force. So what we're going to look at in the Standard Model is the electromagnetic force, which you guys are all experts at because you have been through Physics 4B, the nuclear weak force, the nuclear strong force, and the Higgs force. So those four forces are part of the Standard Model. And then there's this fifth force, gravity, which so far our best representation is from general relativity, which is not a quantized theory. Now what this picture is showing is, if I've got two particles in nature, we know from our discussion of different forces, sometimes forces are attractive, sometimes forces are repulsive. The way that quantum physics, particle physics, takes care of forces is the forces are made out of particles, the same way that electrons and protons and neutrons make up matter. Particles like the photon, the W, the Z, the gluon, they make up the forces. And so what this is showing is, let's say this person's an electron and this person's an electron. How would an electron interact with another electron? And what they could do, now this shows them throwing pillows at each other, which I don't know if that's the best description or not. But let's say they're both holding onto the same object. If they had an object together that they could both reach out and grab onto, they could exert forces on each other by either pushing on that or pulling on it. So if they both pull on that intermediate object, it would draw the two of them together. And that's what's shown down here with these pillows. So here they're grabbing hands and they're pulling towards each other. They're using the force particle to transfer a force in a way that it draws the particles together. And that's why the pillow example is a little harder here. If they're both holding on to something, then they could both push away. And so they could push away from each other, or they could use that intermediate particle, a pillow, to draw towards each other. So that's how we view forces in nature. And here are the diagrams we're going to be using. So this is something called a Feynman diagram, and we looked at those. When we did radioactive decays, we looked at Feynman diagrams, And we use those to understand, in particular, beta minus, beta plus, and beta neutral. We wrote down a Feynman diagram for each of those different types of reactions. Well, in this chapter, we're going to be looking at in even more detail. And so here is an electron coming in and interacting with another electron through this intermediate photon. Now, photons are understood to be the carriers of the electromagnetic force. Now, when we see a photon, those are photons that have terminated inside our eyes or on some detector. The photons we're talking about here are interacting exclusively between other particles. So we don't directly observe those, we just see the effects. And they're referred to as virtual particles. In this case, it's a virtual photon. It's not being picked up by any detector, but we can measure the properties of this photon by measuring the energy and momentum of the electrons going in, measure the energy and momentum of the electrons coming out, and whatever the differences are would have to add up to be the energy and momentum of the intermediate photon. So with energy conservation and momentum conservation and even angular momentum, spin conservation at each of these vertices, that's enough information we can go in and analyze what the properties are for that photon. When we do that and carry out the calculations, those calculations reliably predict the observations that we make. So again, it's one of those situations where, hey, here's a series of steps we go through in order to calculate the probability, say, of this reaction occurring. And when we follow the rules that we've set up for ourselves, we can make a series of predictions. We can go into the laboratory, run those experiments. Those experiments have been run now for 50, 60 years, 70 years, and it works. It really works. It matches up with what our observations are. Now, one thing I want to point out on this Feynman diagram is there's kind of different, traditionally there's different ways the Feynman diagrams get drawn. Often they get drawn as time goes from bottom to top, with position going this way. So in this case, it's the particles at the bottom going into the reaction and the particles at the top coming out. I'm mostly going to draw the diagrams from left to right, which I feel like is something you guys are probably more familiar with. And I don't see any good reason to tip the time axis in this chapter compared with what we've been using everywhere else. So anyway, we'll try and pay attention to that as we go through. Make sure that we've got the timing directions set up. All right, here it is, the standard model of particle physics. So particle physics starts out by saying, hey, everything's made out of particles. The matter stuff around us is made out of particles. The forces holding everything together is made out of particles. Now, the matter particles, it turns out, this is kind of interesting, they all turn out to be spin-half particles. You know, we started by saying, hey, electrons can be spin up, spin down. Well, it turns out that all of the matter particles, the protons and neutrons, can be spin up, spin one half, and spin down. All of the fundamental particles are these spin half type particles. The protons and neutrons actually aren't fundamental, but so let's take a look and see what we've got. The matter particles divide into two separate categories, referred to as leptons and quarks. So now lepton means light particle, the low mass particles, and on average the leptons are lower mass than the other particles we're going to run into. So let's see what we've got here. We've got the electron, so that's good. We see that. There's a neutrino here. Now the electron and the neutrino make up what we refer to as the first generation of leptons. So these leptons exist in three distinct generations, and they come in pairs of particles. So there is a charged version, which in the first generation we call that the electron, and its neutral partner is the neutrino. And those particles are closely related to each other. In some sense, they're really all kind of the same particle. It's as if these 6 different leptons are really just one particle that we call a lepton, and that particle can change its identity in different reactions. Because when we do run reactions, and we've seen this in beta decay, beta plus, beta minus, beta neutral, electrons and neutrinos can kind of turn into each other. The second generation of leptons consists of a muon. Now there's a second neutrino. So we have to start putting subscripts on our neutrinos to keep track of the different types. The muon turns out to be, in many ways, just an identical version, another electron basically, but it's much heavier. It has about 200 times as much mass as an electron. So it's kind of interesting. I mean, it's kind of mysterious. We don't know why any of the fundamental particles have the masses that they have. But it's kind of just a duplicate of the electron. So we place that in what we call the second generation. Now, there were questions. Do we really have 2 distinct types of neutrinos? Or is there just one type of neutrino? And experiments, again, from many years back now, probably in the 50s or early 60s, clearly pointed out that these are 2 distinct flavors, is what we call them. So 2 different flavors of neutrinos. So altogether we have 6 flavors of leptons. We have 3 charged flavors, the electron, the muon, and the tau. And on the tau, we don't typically put the on. We don't add that on the end. Kind of interesting. Electrons, muons, taus. The muons are like 200 times as heavy as an electron. The taus are like 3,500 times as heavy. So again, there's no obvious reason for the way that the mass numbers show up. We don't know why they have these masses. So we're going to list all of these leptons on the lower side as having a charge of -1. There is a third distinct neutrino that goes along with, makes a pairing with the tau. And so we've got an electron neutrino, a muon neutrino, and a tau neutrino. And all of those are neutral. Now, this is probably as good a point as any to point out that I feel like in a lot of textbooks, college textbooks and physics textbooks have kind of their dedicated chapter on particle physics. But I think it's always told from kind of a historical perspective. And in many ways I feel like it's the way they're explaining things is really out of date. It's if somebody came back from the 1960s or 70s and kind of explained the current state of the Standard Model at that time. So I think it's always good to look, once we've figured out how everything fits together, let's just do a general overview. So one of the warnings reading through the textbook is don't get caught up with all of this historical stuff, many of the items which aren't really important to us at all. They were ways people were thinking of things at the time, but that's no longer the way that we really think about it. So ideally, pay closer attention to the lectures, take notes from this. I'll be sending out PDFs of all these. And then look at the homework problems. And the homework problems that I've assigned, for the most part, I think are doable mostly from the lectures. So we've looked at the leptons, 6 different flavors of leptons. Well, there are 6 different flavors of quarks. So, and these kind of, well, we'll get more to that. But the quark flavors have been labeled as the first generation of quarks, the simplest, lowest mass quarks, were called down and up. And that seems simple enough. Down and up quarks were used to explain protons and neutrons. It turns out that the up quark was imagined to have a charge of +2/3, and the down quark -1/3, and experiments have suggested that these are accurate representations of what's really going on. So a proton is made up of 3 quarks, flavors up, up, and down. Now, 2 ups and a down, that would be plus 2/3, plus 2/3, minus 1/3. That would give us a particle that has a charge of plus 1. And that would be the proton. Now, the neutron is also made of 3 quarks, but the flavors are up, down, and down. So they're similar, but whereas the proton has 2 ups, the neutron has 2 downs. When we add those charges together, plus 2/3, minus 1/3, minus 1/3, well, that gives us something that's 0. So this is kind of interesting that the up quarks have and the other quarks, the other quark flavors also follow this pattern. All of these up-like quarks have charge of plus 2/3. All of the down-like quarks have charge of minus 1/3. Even though they have fractional charge based on the fundamental charge E, all the combinations of quarks always work out to be integer values. So if you take 2/3 and minus 1/3, and you try all the different ways you can take 3 of those and add them together, you always get an integer value. So all the observed particles in nature have integer values of charge. The quarks, individually themselves, are never observed, not directly. So we have to infer the presence of quarks from running different kind of experiments, shooting beams of electrons at protons and neutrons, other types of reactions. So this is our understanding. Now, what's holding these quarks together inside the proton and the neutron are what we call gluons. And yeah, the word gluon is based on the word glue. It's just holding something together. And the gluons make up what we call the strong force. So the strong force applies to all of the quarks, but not to the leptons. Leptons don't feel the strong force. So electrons and neutrinos are unaffected by the strong force. But all of these different quark flavors are held together by gluons, which make up the strong force. Now, to finish out these generations, we said the first generation were listed as down and up. The second generation has flavors of strange and charm. Now, the way this worked with the naming is, first of all, a lot of this stuff was discovered during the 60s. And it was a period where people were trying to come up with kind of whimsical names for different things, that we didn't have to, name things kind of in the standard, some kind of standard protocol. So these were named down and up. Strange was because it turned out that particles with a strange quark had different decay properties. They tended to take longer to decay, and hey, that was strange. And then theorists took a look and said, look, they started to see this pattern of different generations. Now at the time, there was no observed third generation. So what they were looking for was to fill this one missing point in the second generation, and another quark that behaved like the up quark. And so they named it charm because if they discovered this particle, it would make all their theories work like a charm. And that's how the naming went. Now, for the third generation, theorists came up with the words, or the names for these quarks, flavors, of beauty and truth. And so you've got these 6 flavors, down and up, strange and charm, beauty and truth. Now, it does turn out that since that time, by the time, actually, that the truth quark was discovered, researchers had already become, I don't know if it was embarrassed or what, but instead of beauty and truth, it's more common to refer to these as bottom and top now. So anyway, some of these whimsical names on these different properties. So again, we talk about these as flavors, 6 different flavors divided up into 3 different generations, and then uh, the neutrino-like particles that have no charge, the electron-like particles with -1 charge, the up-like quarks plus 2/3, the down-like quarks minus 1/3. And that's it. That's all the matter particles. Everything is some combination of either leptons and quarks. Now, another question we could ask is, well, what's stable? If we've got all these other particles, why do we never hear about them? And it turns out that the higher particles, the different generations, are kind of separated by different masses. As you move from one generation to the next, the masses go up. And sometimes they go up dramatically. As we were saying, the electron's like half an MeV, the muon's at 105 MeV, and the tau is like at 1787 MeV. So the masses can go up dramatically. And because of that, these higher mass particles decay into the lower mass particles. The weak force enables a particle to change from one flavor to the next. The strong force doesn't let that happen. The electromagnetic force doesn't provide for that. But the weak force does allow that heavier quarks or heavier leptons can decay step by step into lighter quarks. Doesn't have to be completely one step at a time. They can jump. So pretty much all the material around us consists of the first generation. Unless we're looking at something in a laboratory under extreme conditions, or we're looking at something astrophysical, possibly under extreme conditions, these other heavier generations just don't survive very long. So of all the leptons, the only lepton that is, the only leptons that are stable are the electron. Now the electron, it can't decay into anything else because it's already the lightest lepton, or the lightest charged lepton. So there's nothing the electron could further decay into. It's stuck. That makes it stable. And then the neutrinos are in some sense stable. Now neutrinos can there's this process called neutrino oscillation, where a neutrino can keep changing different states among the three flavors of neutrinos. So it's a quantum effect where the particle, the neutrino, doesn't quite make up its mind whether it's an electron or a muon or a tau neutrino, and so you get these neutrino oscillations. If you remember back to the previous chapter when we were looking at fusion, and we said fusion reactions inside stars generate neutrinos, and we can tell that the core of the star still is undergoing fusion actively by measuring the number of neutrinos. For many years, the earliest neutrino detectors only measured 1/3 of the theoretical value. Now, researchers didn't immediately think the sun was shutting down, but what they did wonder is why their detectors were only able to pick up 1/3 of the neutrinos they were expecting. And now what we know is this. At that time, researchers expected that since the reactions inside the sun, the fusion reactions, exclusively produce electron neutrinos, that those should all be picked up by their detectors. But it turns out that we now understand neutrinos undergo oscillation, basically changing from one flavor to another. So by the time those neutrinos have reached Earth, what originally started out as purely an electron neutrino now has a 1/3 probability of being an electron neutrino, 1/3 probability of being a mu, and 1/3 probability of being a tau. And that means our detectors only picked up the electron neutrinos, and that was only 1/3. So it's one of those situations where, we keep getting this number, 1/3, what could it mean? And now we understand. Now we have detectors that can measure each individual type of neutrino, and we can see that 1/3 of the original neutrinos are showing up as electron, 1/3 as muon, 1/3 as tau. So again, there's just a whole list of experiments that you look through, and so this standard model, I'm going to say by 1970, it was mostly in place. So in 1970, 4 of these particles had been discovered. The third generation had not. Probably 3 of these had been discovered. So think of the number of predictions here. Researchers by 1970 were predicting the existence of at least one more quark and possibly future generations. Now it turned out that one by one, the charm quark and then the additional third generation particles were all discovered over a period of 20 or 30 years. That's quite a span, but the predictions just kept panning out. Now there have been searches for a 4th generation, and so far there's no indication that there's a 4th generation. Now, we've run experiments that exclusively are able to look just for the neutrinos, and remember the neutrinos have really low mass. So if there is a 4th generation, we would expect there's a 4th generation neutrino, and by now we would have seen it. And we haven't. So you'd have to say the evidence right now kind of suggests that there's only 3 generations of leptons and 3 generations of quarks. We'll see. Again, the standard model has just been amazingly successful. Now, about the strong force. So let's talk a little bit more about the protons and neutrons here. The strong force is made out of gluons. And the strong force is based on a property called color. So in the same way that in electromagnetics, particles are said to have an electric charge, in chromodynamics, which is the theory of the strong force, quarks are imagined to be in either a red state, a green state, or a blue state. Now the red, green, and blue, those are just arbitrary names. It's kind of the same idea as when we say electrons can be spin up or spin down. And that is an attribute related to angular momentum. Here, it just has to do with what's called a color state, and there's 3 of them instead of 2. There's 3 distinct color states. There's a red state, a green state, and a blue state. The strong force only works, it's only attractive, if you take a quark from each of those 3 color states. So I've got to have one quark that currently is in the red state, another quark that's currently in the green state, and then the third quark has to be in the blue state. That is one of only 2 combinations of stability that we observe for quarks. So that's kind of interesting too, I guess. One of only 2 possible combinations, maybe depending on how we count, would be quark, quark, quark. Now another item that we might want to mention here is we've written down all the particles, but for every particle that we wrote down here, there's an antiparticle. So for example, we've looked at anti-electrons, we've looked at anti-neutrinos. What would an antiproton be made of? And it's made out of 3 antiquarks. So the same way that we can get 3 quarks in one of these red, green, and blue states, we can get 3 antiquarks in what's referred to as an anti-red, an anti-green, and an anti-blue state. And so we can have antiprotons, and we can also have antineutrons. Antineutrons are made of anti-ups and anti-downs. So if you remember, I think at one point we've mentioned that neutrons, even though they're electrically neutral, neutrons have a magnetic field. So neutrons display magnetic properties. How is that possible for a neutral particle? And it's because it's made out of quarks, and those quarks are charged. So the charges on the quarks all cancel out to 0. 2/3, minus a third, minus a third, no net charge. But each one of those quarks is a spin-half particle. So each one of the quarks has its own magnetic field, and the magnetic fields don't cancel out. So, so neutrons have magnetic properties to them because of the quarks that make them up. Here's a diagram of the different patterns of quarks that we observe. Now, we talked about the quark-quark-quark combinations. Up-up-down flavors make a proton, up-down-down make a neutron, and those are the masses of those particles. There's a couple other combinations. The other combination here would be what we call antibaryons. Now, an antibaryon would be 3 antiquarks in anti-color states. That's kind of the same thing, right? So I don't know if you count that as a separate classification, but it is good to remember that we can make antibaryons. Now, we should also mention this. The proton and neutron are the lowest mass combinations of all the baryons. And even the neutron, if you remember, is not stable. A neutron left to itself decays within 10 or 15 minutes, and it decays into a proton by that same reaction that we looked at in beta decays. So there's really only one baryon that's stable, and that's a proton. Every other baryon in nature, the neutrons and all of the other color combinations, all of the excited states, there's just hundreds of these particles that have been identified that are made up out of quarks. All of the heavier baryons eventually decay into a proton. And most of them do it pretty quickly. So within a matter of, except for the neutrons, so within a matter of seconds, all of the other baryons that we generate decay back down into a proton. And they're giving off other particles along the way. So one stable baryon, the electron was stable. The combination of neutrinos makes kind of one stable particle, and that's it. The photons are stable. I guess we could say that too, although photons are going to get absorbed at some point, but they don't undergo decay. Now, none of the mesons are stable, and mesons are quark-antiquark pairs. So it seems funny to have a particle made up of a particle-antiparticle. You would think, well, that's not going to last long. And the longest-lived mesons only survive a couple of microseconds. And those longest-lived mesons are referred to as the pi plus and the pi minus. And what they are is the pi plus is a up quark and an anti-down quark. So let's see, that would be plus 2/3. Now, the down quark would be minus 1/3, but this is an anti-down, so it's plus 1/3, and that gives it 1 full charge, so that's plus 1. This is its kind of anti-particle. If we reverse the anti-sign, so it's anti-up, and these lines over the top, those are anti-signs. The anti-up and the down, then that reverses the charge, but it doesn't affect the mass. So the mass of the particle-antiparticle pairs, the mesons, are the same. They're not stable. These are the closest thing to being stable. Again, they have a lifetime of a few microseconds. Now there's a neutral version of the pion, and that's made out of an up anti-up plus a down anti-down. It's one of those quantum oscillation things where it's a linear combination of the up anti-up state and the down anti-down state. So at any instant, if we did a measurement and reacted, it's kind of a 50-50 chance that we would observe it as up anti-up, and a 50% chance it would be observed as down anti-down. And that's a little lower in mass because of the way the nuclear force is holding those together. Okay, that's probably a good place to go ahead and take a break, so we'll wrap things up right here. But that's a pretty thorough overview of the standard model.